For section 3.5, we are going to prove that the Pythagorean theorem is always true whenever you have a right triangle. When we do this, we're going to construct viable arguments and critique the reasoning of others. So when I say that we're going to prove it, we're going to create a proof, which the mathematical definition of a proof is a deductive argument for a mathematical statement. So basically, saying that simpler is you have to use only information that you know is true, and then you can use that information to make an argument that a different mathematical statement, like the Pythagorean theorem, is also true. So the big idea is that in math, you cannot assume anything is true. You can never, ever assume it's true. It always has to be proven. So you have to use old information that has already been proven, or that's already a fact, to prove new information. So that's what we are going to do today. So for the Pythagorean theorem, we have a right triangle. And the sides of this right triangle are going to be called, here's our right triangle, they're going to be called A and B. Now, A and B are the legs. That's what they're called. They're called the legs. And the legs of the right triangle are the two sides that form the right angle. The other side that's kind of in that on the opposite side of it is C. C has a special name called the hypotenuse. The hypotenuse is the longer side. It's always going to be the longest side. It's the side that's opposite from the right angle. So it's opposite of the right angle. It's always going to be opposite of the right angle. It's always the shorter sides that create that right angle, and the longer side, that's the hypotenuse. All right, so that's the Pythagorean theorem, but how are we going to prove this? Just a reminder of what we did yesterday. We created a square, and then on that square, inside of it, we created 4 right triangles. And when we created those, it then created a square inside of that as well. So we figured out the area of the big square, and we figured out the area of the triangles by being able to count the distance around the outside of the square. And then we took the area of the big square minus the 4 triangles to get the area of the small square. And then from there, we figured out that last, the hypotenuse length of those triangles, or the side length of the squares. We're going to use this same sort of thing today when we prove the Pythagorean theorem. However, yesterday we used numbers and we used actual side lengths, and today we cannot do that. In order to prove that this is always true, we have to use variables. If we use side lengths, if we use actual numbers, then that proves that it's only true when the side lengths are that exact length. It doesn't mean that it's true if they're different lengths. So when we use variables, that means that I can choose any number for A and any number for B, and if I square them and take the sum, then it's always going to equal C squared. So to prove this, we're going to start with a right triangle, and that right angle is right here. We're going to take that right triangle and we're going to set it down and we're going to rotate it around until we create a square. And then that creates a smaller square inside of it also. Notice that this is the same diagram that we drew in class yesterday. So our end goal here is to say that the area of the 4 triangles plus the area of the small square is equal to the area of the whole square. So if we take all the parts and add them together, we get the whole. And that is what our goal is. So the area of the 4 triangles plus the area of the small square is going to be equal to the area of the whole square. All right, so let's go ahead and do this. So to do this, we have the same diagram, and like I said before, we're going to be writing all of this stuff out with variables, not with numbers. So we're going to start by finding the area of the big square. In order to find the area of a square, remember the area is length times width, we need to know what the length is and we need to know what the width is. So when I'm looking at the length, if I know that this is A and this is B, then the whole side length is going to be A plus B. So I know that the length of one side of the square is going to be A plus B. The area of the big square is length times width. If this is A plus B, then this is also A plus B. Because the sides are always the same length on squares. So if I'm going to take the length, which is A plus B for area, and it's one length, so I'm going to put parentheses around it to group it together, times the width, which is also A plus B. Once again, I'm going to put parentheses around it to group it together. This gives me the area of the square. Now the next couple steps, we're just going to go through and we're going to multiply this out and we're going to simplify it. So we've never actually seen something like this before. So what we're going to do is a special kind of distribution called double distribute. So we're going to double distribute right here. That means that we're going to take every part of the first parentheses and distribute it through or multiply it by every part of the second parentheses. So I'm going to take the A and I'm going to multiply it, or I'm going to distribute it to both parts of the second parenthesis. So when I do that, I get A times A, which is repeated multiplication. That is an exponent, so I have A squared. And then A times B, which I can just write as AB. So far I have A squared plus AB. Now I'm going to do the same thing with the B. I'm going to distribute it to the second parenthesis. So then I have plus BA, and then B times B, which is B squared. So here I have A squared plus AB plus BA plus B squared. Now I notice that AB and BA have the same variables in those, but they're in different orders. But if I think about that, I have two variables right next to each other, which tells me that that's multiplication. And I know that multiplication is commutative. So I know that I can multiply it in any order and get the same thing. So if AB is equal to BA, I'm going to go ahead and rewrite BA as AB. So so that I see where to go from here. So I have a squared plus ab plus b squared. So now I notice that I have two terms that are the exact same. So if I have two ab's, I have repeated addition, then ab plus ab becomes 2ab. So this last line, I have a squared plus 2ab plus b squared. Now between my three parts of this, none of them are like terms, so this is all I'm doing on this one. So now I have the area of the big square. My next thing I need to do is find the area of one triangle. So if I'm looking at this triangle right here, I'm going to zoom in on it. I know that the area of a triangle is 1/2 AB. Is 1/2 base times height. Well, I see that the base of this is B, and the height is A. So I have 1/2 BA. This is multiplication, so it's commutative, which means I can multiply in any order. So I'm going to go ahead and write this as 1/2 times A times B, just so that it's written in alphabetical order. So the area of the triangle is 1/2 AB. Now I need to find the area of the four triangles. So if I know that the area of one triangle is 1/2 AB, and I know that all four triangles are the same area because they both have the sides of the legs of A and B, then I know that the area of all four triangles is just going to be the area of one triangle times 4. So I'm going to take 4 times the area of one triangle, or 4 times 1/2 AB. Now this is all just multiplication, and I see that I have two numbers in here that I can multiply together. I know that 4 times 1/2 is 2. So the area of the four triangles is 2AB. I'm getting close to the end here. The last thing I need to do is figure out the area of the small square. So now I just have the area of the small square to get. I know that the area of a square is length times width. I see that the length is C and the width is C. So the area of the small square is C times C, or C squared. If I think back to my goal, I wanted to find the area of the four triangles, the area of the small square, and the area of the whole square. Well, let's look and see what we have. I have the area of the whole square right here. I have the area of the four triangles right here. And I have the area of the small square right here. So now I just need to put that together. I have the area of the small square, the area of the four triangles, and the area of the big square. So I'm just going to move those numbers right there. So when I do this, I know the area of the four triangles is 2AB. The area of the small square is C squared. And then the area of the big square is A squared plus 2AB plus C squared. Plus B squared, sorry. So I have 2AB plus C squared equals A squared plus 2AB plus B squared. So there's a lot going on here. I notice, though, that I have 2AB on both sides of the equal sign. So I'm going to see what happens when I get rid of those. If I subtract 2AB from both sides, on the left side I cancel those out and I'm just left with C squared. On the right side I cancel them out and I'm left with A squared plus B squared. All of a sudden I recognize this as Pythagorean theorem. I'm going to go ahead and write it this way, since this is the same thing. I have A squared plus B squared equals C squared. That's my Pythagorean theorem. I'm done with this proof. So once again, what we did is we took a right triangle, just any regular right triangle. We didn't put any lengths on it, so this stands for any right triangle in the entire world. We rotated it around, we made a square out of it, which is what we actually did yesterday. And then from there, we just found the area of the triangles and the area of the small square that they created and added those together to equal the area of the big square. And when we did that and simplified it down, we were left with the Pythagorean theorem. So this is now proven. You can take this now and do your homework. On your homework, you just have the layout for the proof, just like we did in the notes. Do as much of it on your own as you can, and then check your notes as you need to complete it. Really think about what you're writing, though, and try to make as much sense of it as you can. And then that's all you need to do for your homework. If you would like a challenge, on the back of the homework is just the diagram, and I do not have it laid out for you, so you can see how well you do that. You don't need to do both sides. You can do one or the other. If you would like, however, you can try both sides and see if you can do it on your own. That is all for this section. So as always, if you have any questions, definitely let me know.